Continuity. Before we get into the formal definition for continuity, let's first establish what we're talking about when we reference that a function is continuous. We need to know that continuity is a local property, meaning that when we say a function is continuous, we're referencing at a certain point or across a certain interval. So a function is continuous at a point. Could be x equals a, or along some interval. So when you hear that a function is just the term a function is continuous, that's referencing along its domain. So if you see a function is continuous, and it doesn't specify at a certain point or a specific interval, you just assume it's talking about along its domain, not necessarily across all real numbers. And all real numbers, again, would be from negative infinity to infinity. Now, if the domain is all real numbers, well then yes, it is continuous across the interval negative infinity to infinity, but I don't want you to assume that if you just see that a function is continuous. So make sure you check its domain if it doesn't specify where the function is continuous from. So let's look at this basic graph that I have set up for us. So we have a piecewise here. We got some discontinuities going on, but I want to discuss like a really, really simple definition of continuity before we get into the more rigorous formal definition. If I take my pencil and I want to test for continuity, if I trace along the graph, as long as I don't pick up my pencil, or I should say, when I'm tracing my graph, it is continuous along the interval in which I never have to lift my pen or pencil. So if I start at A over here, and I'm tracing along this function's graph, I could say it's continuous from A to B, because I never had to lift my pencil. But as soon as I have to lift to get to the next part of the graph and continue it in order to continue the trace of the function curve, I can see that I have a discontinuity in this gap here because I had to lift up my pencil to start at this next point up at the top. But I could say that it's continuous again on the open interval from B to C. But then as you can see, I have a hole, so I have to lift up my pencil again. So I would say there's a discontinuity at C because I had to lift up my pen. But then I could say it's continuous again from open interval C to a closed interval D here. So we could say that it was continuous from A to B, closed on both. Then I had to lift it up, so it would be continuous on the open interval from B to C, and then continuous again from C to D. Okay, so that's like a very basic definition that you can use to help you out if you want to know where something's continuous. If you can just trace from along the interval, if they claim that it's continuous from A to B, if you can trace the whole thing without having to lift up your pencil, I guess you could say that it is. So now let's look at the more formal definition. So we're now going to discuss the test for continuity. And from this test, we will derive the formal definition. So you need to know this test and this definition like it's the back of your hand, okay? This is something that we just need to be rock solid on. So the first thing, this is for a test at a certain point. So let's say at x equals a. The first thing is we want to establish, does the limit of the function as x approaches a exist. Okay, and if we're trying to test that, remember graphically, this is a two-sided limit. So if we want to establish it exists, we are going to have to establish that the one-sided limits are equal. So we want to check to see if as we approach from the left and from the right, we get the same thing. Now, why do we want to test for that? Well, if we go back to our example graph, we can see that at a point on the intervals where we did have continuity, let's say I'm looking at a point within this first interval here, we can see that at this point, the limit exists. Like as we approach from the left and from the right, we arrive at that same coordinate. But if we were to say test continuity at this point, when we come from the left and when we come from the right, we're not arriving at that same coordinate. So that would be an example. This gap here shows failure for continuity based on the first step in our test. So we want to make sure that the limit exists if we have continuity at a point. The second thing is we want to test to see if the function output exists. So does f of a exist? So this is asking, when I plug in a to our function, do we get a defined answer? So is this defined? Now going back to our example, at this green point here, we can see that the function's defined there. We get an output. If I plug in this value, whatever that is, the output exists, okay? But if I go over to point C, we have a hole at C, right, at this point over here. So f of C, in this case, that doesn't exist. Okay, there's no function output with that, okay? So that's our second question. The third question is, does the limit of f of x as x approaches a equal the function output? If we say yes to all three, then we can say, so yes to all three. Then we can say the function is continuous at x equals a. So what do we mean by the limit equaling the function output? Going back to, we'll just pick another random point. Let's say we're in this location here. When I look at the limit, let's call this point E, we can say that the limit as we approach E from the right equals the limit as we approach E from the left. Okay, but we can also say that the limit, which would, again, if you recall, is the y coordinate. So this would be, this coordinate would be E, f of E. That's our coordinate there. F of E is the limit, and it's also the function output. So the output equals the limit. Now, where does that break down? What's an example of having a limit existing, but the function output not equaling that? Well, if we go back to this open circle on point C, we can see that the limit exists at C. So if I approach C from the left and from the right, we can see that the limit exists. But let's say the function output, we had a circle up here. So in this case, this coordinate C, f of C in this case is not equal to what that limit was, right? So this point here, where we're approaching, is not equal to what the actual output is. So that's an example where the output doesn't equal the limit. Now, we asked three questions. So what's the actual definition for continuity? It is basically, or not basically, it is that third question. So this is the definition for a continuous function. And you should know this. The limit of f of x as x approaches a equals f of a. So simply put, the limit equals the output. Very important. Okay, the limit of a function equals the output. That is our definition for continuity. And that will be on the interior of an interval. So let's just make that note. If we're looking at continuity at an endpoint of an interval, we'll just make one small adjustment. So we'll say at an endpoint of an interval, the definition for continuity is for the left endpoint, the limit of f of x as x approaches a from the right, again, from the right moving left, so that will get you to the left interval, or sorry, left endpoint of the interval, has to equal the function output at that point. And then the right end of the interval, we're coming from the left, so you can expect our left-handed limit. Again, coming from the left, moving right, that will get you to the right endpoint. So those are our definitions for endpoints of intervals if we want to test for continuity there. So again, you really need to know this definition right here. So memorize that, understand it. We'll go through some formal examples in class, but need to know definition for continuity. So now that we know how to define continuity, we're going to look at types of discontinuities. The first type of discontinuity is removable. So removable discontinuity is a hole in the graph. Okay. And a more formal definition will be when the limit of the function as x approaches a just does not equal the function output at a. That's the definition, okay? So the limit exists, but it's just not the same as the function output. So this is our definition for a removable discontinuity. Now, just a quick recap from pre-calc. If you remember when we have rational functions, so we'll just put a little note off to the side. An easy way to find them with rational functions. We're looking for cancellations. So cancellations reveal holes. Okay, so example, let's say we have f of x equals x squared minus 1 over x plus 1. When we factor the top, we get this cancellation with x plus 1. So we know there's a hole at x equals negative 1. So we take what's canceled, we solve it, and that reveals where the removable discontinuity is. Okay, but again, formal definition, the limit exists at the point, but it doesn't equal the function output. Next is the jump discontinuity. Oh, so we'll just draw a little picture. So we might have something like that. Okay, and we could have an output still exist at that point, but just again, it just doesn't equal the limit. So a jump, we have like a vertical gap. Formal definition, maybe you can think of it on your own if you want to even pause the video and try, but we'll have actually let me draw a picture and we can come up with a definition on our own. So if we have, like we saw in our picture, we have this vertical gap here. How would we define the jump discontinuity? We might say that the limit of f of x as x approaches, we'll say that this is at point A, at x equals A. We might say the limit as x approaches A from the left just does not equal the limit of f of x as x approaches A from the right. Okay, so that will be what we're looking for when we're trying to discover a jump discontinuity. We're going to be looking for this limit definition here. And this is going to pop up often with piecewise functions. It'll happen with some absolute values, like, for example, absolute value of x over x, step function. But that's where we can see a lot of jump discontinuities. Most often we'll see them with piecewise. The infinite discontinuity will look something like, there's several iterations of this, but let's say we're at some point x equals A, and then as we approach A, the function goes off towards infinity. And again, it could go towards negative infinity, maybe one side's going down, one side's going up. But as you can see, it's not continuous at A because these 2 points won't reach, or these two pieces of the graph won't touch each other. So from a limit definition, we're looking at the limit of f of x as x approaches A from the right is going to equal plus or minus infinity. Or we could have the limit as x approaches A from the left of our function equals plus or minus infinity. Now, this should look pretty familiar to you. What do we have here? None other than the definition for a vertical asymptote, which I asked you to know. Okay, so for infinite discontinuities, we're looking for that limit definition there. When we approach the constant, the limit goes to plus or minus infinity. We know we have an infinite discontinuity there. And then the last one is an oscillating discontinuity. Oh, another way to determine this infinite discontinuity, let's say when we're evaluating the limit, let's make a note here. It's not as thick. We're checking what values result in a number over 0 when evaluating a limit. That will be location of infinite discontinuity. Then the last type of discontinuity is oscillating discontinuity, which is best seen through a picture. So I'm going to draw a quick coordinate plane here. An example graph that results in one would be, or an example function would be like if you had f of x equals sine of 1 over x. We can see at 0, we're going to have a problem there. And if you took a look at the graph, you would see that when it gets towards 0, it starts oscillating really quickly. And what's happening as you approach 0, it keeps jumping back and forth between plus or minus 1. So because you can't determine where it's actually headed because it's fluttering so quickly, we say that there's actually no, it's not continuous there because we can't say that as the limit approaches 0, the output approaches the same value of the limit. So we're going to say we have a discontinuity at x equals 0, and the type would be oscillating because it's jumping back and forth between output values. Okay, so those are all types of discontinuities. And to finish the video, we'll cover properties of continuous functions. so that when you have a function that you are unfamiliar with what it actually looks like and you're asked to determine whether or not it's continuous, you can help, or you can make a decision with the help of these properties. So if functions f and g are continuous at x equals c, then for the sum, it says, well, if f and g are continuous, then the sum of the two functions is also continuous. The difference, you can expect the difference between them is continuous at x equals c. The product, if two functions are continuous, then their products are continuous at that point. The constant multiple, if you have a continuous function, you multiply it by a constant k, then that is continuous, right? Because that just scales the function or dilates it. The quotient, their quotients will be continuous as long as, you probably guessed it, g does not equal 0 at that point. And then composites is going to be if f is continuous at x equals c and g is continuous at f of c, then g of f of c is continuous. So when we have a composition, if the inner function's continuous at c and the outer function's continuous at the value that the inner function produces at c, then we have continuity for the composite function. So an example to kind of illustrate all of these at once, let's say we have a function f of, we'll just call it y actually. Let's call it y equals absolute value of x sine x over x squared plus 2. And we're asked to figure out if this thing is continuous at some point. So let's break down this function into pieces and use those properties above to determine if this function would be continuous at some point. So in the numerator of this rational piece, we have x times sine x. So if I look at x and sine x as the two functions and they're being multiplied together, I can use that product property. And x is continuous for all real numbers. And sine x is also continuous for all real numbers. So therefore, the product of the two is continuous for all real numbers. So we took care of the numerator. And the denominator, x squared is continuous for all real numbers. The constant 2 is continuous for all real numbers. So their sum is continuous. And if the numerator and denominator are continuous for all real numbers, then their quotients should be continuous. As long as x squared plus 2 does not equal 0. So we can figure out when x squared plus 2 would equal 0. If we solve that, we get x squared equals negative 2. Then we get x. Oh, why did that change? So we're going to have negative 2. Take the square root. We'll get x equals plus or minus I square root of 2. So this isn't even a real number. So where we have discontinuities is in the imaginary realm. So we don't even, this. So that means this is going to be continuous for all real numbers for the quotient. And then lastly, we have this inner function, and we have a composition with the absolute value function. So we can think of this original function was a composition between two functions, where g of x is the absolute value of x, and f of x was that inner piece. And we just determined that f of x would be continuous for all real numbers. And we know that if it's continuous, then g, when I evaluate g at f, will also have continuity based on that composition rule. Absolute value is also continuous for all real numbers. So that means that y is continuous for all real numbers. So that's just breaking it down piece by piece using those properties to determine that y is a continuous function across the domain, or sorry, across all real numbers, negative infinity to infinity. So that's how you can utilize those properties to your advantage. And that will conclude the video on continuity. Again, the most important thing from this video is know your limit definitions for discontinuities, how to identify them. But even more importantly, know the definition for continuity. The limit at a point needs to equal the output at that point. And we'll do plenty of examples to illustrate how to use that, but something that you have to know.